Welcome to the first re-recorded QOD video of the 2020-2021 AP Chemistry season. I spent a lot of my time this year listening to the various bands playing in the tent downstairs, and so I thought I would start with a quick tribute to the St. David's Band tent. And two of the class periods that I hear a lot of music from are fifth period and first. So when I hear fifth period playing, uh, this is what I tend to think of. And this is what I think of when I hear the first period band.
Never had one lesson.
All right, well, what the video is actually about is something called Dalton's law of partial pressures. And this was worked out by John Dalton, who is the same John Dalton that gave us Dalton's atomic theory. And in fact, a lot of the early chemists in the 18th and 19th century were working with gases. Dalton was a particular fan of the atmosphere and climbing up mountains to measure atmospheric pressure at different altitudes. He was kind of the first person to figure out that the atmospheric pressure varied with altitude. Avogadro is another guy who worked in gases, as we've learned. And in fact, it was in characterizing gases that was as a result of a lot of that work that that people were able to work out this idea of the law of conservation of mass, and that led Dalton to his atomic theory. But what does Dalton's law of partial pressures actually say? It says that the total pressure, so if I've got a mixture, a gas sample that's not a pure substance, but a mixture of substances, and air would be a great example of this, the total pressure exerted by that mixture of gases is equal to the sum of the individual pressures that each component of the mixture would exert if it was present by itself. So let's kind of disentangle what that means. Simply, the way that Dalton's law of partial pressures is stated is that the total pressure of a gas mixture is equal to the sum of the partial pressures. So again, if we were talking about air, for example, P total would be the total pressure of the air. P1 would be the partial pressure due to nitrogen. P2 could be the partial pressure due to oxygen, et cetera, et cetera, et cetera, for every component of the gas. So we can, if we were talking about air, and air is composed, more than 99% of air is composed of three gases, nitrogen, oxygen, and argon. And the partial pressure, and so let me just back up. So, and talk about what's the point of all this, which is always a good thing to be talking about. Why does it matter if I've got air and air is exerting a pressure of 1 atmosphere? Why does it matter how much of that pressure is coming from nitrogen and how much of that pressure is coming from oxygen and how much of that pressure is coming from argon and other gases? Particularly since they're all jumbled together and they're not actually in there separately. Well, it turns out that it is important, and later this year we'll learn about, for example, what's called Henry's law, which governs the solubility of gases in water, and it's proportional to the partial pressure of the gas in the atmosphere above the water. And you can kind of think that that makes some sense. The solubility of oxygen in water is going to be a function of the oxygen pressure above the water, not the total pressure, because it's only the oxygen that we're talking about dissolving in the water. So this will make more sense as we go forward, but let's just talk a little bit more about Dalton's law. The other thing that we're going to learn here is the partial pressure of an individual gas in a gas mixture is directly proportional to what's called its mole fraction. And this is a different way of expressing concentration, the concept of the mole fraction. It is given the symbol chi, the Greek letter chi. And so the mole fraction of a substance is simply equal to the number of moles of that substance over the total moles of everything of all substances that are in that mixture. And so we can express it like this. The mole fraction of substance A is equal to the number of moles of A in the mixture over the total moles of everything in the mixture. And therefore, we can say that the partial pressure of A in a gas mixture is equal to the mole fraction of A times the total pressure of the mixture. So let's take an example of this, a simple example, air, which we've been talking about already. Air is composed, again, almost entirely, although we talk a lot about carbon dioxide and global warming and other things that are in air, those things only make up really, really, really tiny fractions of the air. The vast majority of it consists of nitrogen, oxygen, and argon. And actually what that does is that tells you how powerful and potent some of these greenhouse gases are, right? That they can exert such an effect on our climate, even when they exist in air as just tiny, tiny, tiny fractions of the overall. Anyway, let's determine the partial pressures of each of these three gases in a sample of air that has a pressure of 1 atmosphere. So we've said that the mole fraction of any gas is equal to the total moles of that gas. The number of moles of that gas over the total moles in the sample. And that the partial pressure of that gas is equal to the mole fraction times the total pressure. Okay, so just like back when we were talking about mass percentages, we would assume we had a 100-gram sample of something that would allow us to turn percents into grams. Now let's say we've got a 100 mole sample of air, and so that means that its mole fraction of nitrogen is going to be 0.78, right? So if I've got 100 moles of air and it's 78% nitrogen, then that means I've got 78 moles out of 100, which are nitrogen. Therefore, its mole fraction is going to be 0.78. And so when I multiply 0.78, which is the mole fraction, by the total pressure of the sample, which is 1 atmosphere, I'm going to get 0.78 atmospheres as the partial pressure of nitrogen. And I can do the same thing for oxygen. So it's going to have a mole fraction of 0.21 times 1 atmosphere total. That gives me a partial pressure of oxygen of 0.21 atmospheres. And finally, for the argon, because there is 0.01, 1% of the air is argon, therefore its mole fraction is 0.01. Multiply that by the total pressure. Its partial pressure is going to be 0.01 atmosphere. Well, that was a really simple example because we can just, because everything adds up to 100%, and it made for a very simple solution to that. Let's look at something where the pressure of the system isn't 1 atmosphere, it's something else, and therefore it's going to require us to do a little bit more calculation. So I've got a mixture of 3 noble gases, xenon, krypton, and argon. That has a total pressure of 6.7 atmosphere. What would be the mole fraction of krypton in the mixture if the partial pressures of xenon and argon are 1.6 atmospheres and 2.8 atmospheres, respectively? Okay, well, let's remind ourselves that what Dalton's law tells us is that the total pressure of this mixture, which is 6.7 atmospheres, is equal to the sum of the partial pressures of the individual gases. That's going to allow us, we're looking for the mole fraction of krypton. First, we want to figure out what the partial pressure of krypton is. And so we rearrange that to say the partial pressure of krypton is going to be equal to the total minus the sum of the partial pressures of the xenon and the argon. So we work that out, and we get that the partial pressure due to krypton in this mixture is 2.30 atmospheres. Okay, well, we've said that the partial pressure of any gas is equal to its mole fraction times the total pressure. And so we now want to solve for the mole fraction of krypton. We know that the total pressure is 6.7 atmospheres. We know that I'm sorry, I'm just doing the algebra here to rearrange this for mole fraction of krypton. We know that the total pressure is 6.7 atmospheres. We just calculated that the partial pressure due to krypton is 2.3 atmospheres. And therefore, we can figure out that the mole fraction is 0.343 for krypton. All right. Let's talk about a topic that your book goes into, and I'm actually going to do a demonstration of this in class, hopefully next week. Um, and this is the concept of collecting a gas over water. Okay, so here we got a reaction in which I'm going to drop a little piece of zinc into hydrochloric acid. This is a really convenient way of generating hydrogen gas in a laboratory. So the zinc gets oxidized, the H plus gets reduced. You wind up with zinc chloride and hydrogen gas, which then bubbles out of the mixture, out of this test tube. And I could collect this. And when I do this, I collect it in a graduated cylinder, which allows us to measure the volume. But you're doing this to keep the atmosphere out. You do this all in a system of water displacement. And so what that means is that when I collect the hydrogen in the graduated cylinder, not all the gas in that graduated cylinder, even though I have excluded all the air, not all the gas in that graduated cylinder is going to be hydrogen because there will also be some water in there. Water has what's called a vapor pressure, which varies by temperature, but a certain percentage of that sample of hydrogen is going to be water, not hydrogen. It's going to be small. It's not going to be like what this diagram is showing, in which like half of what's there is water. It's a very small percentage, but it's not negligible. So let's talk about how that works. Okay, so when I collect a gas over water, there is water vapor mixed in with the gas. And so to find only the partial pressure of the desired gas, I have to subtract the vapor pressure of the water from the total pressure. And this has to do with working out, why would I need to know what the partial pressure of the hydrogen is? Well, then I can calculate how many moles of hydrogen I have if I know, using PV equals nRT. And I can work out yields and things like that. Okay, now you're going to start getting more and more familiar with the appendices on the back of your book. This is not Appendix B, but it's in an analog of Appendix B. I just pulled this image off the internet somewhere, but Appendix B essentially has all this same data, which is the vapor pressure of water at different temperatures. What's nice about your textbooks one is that like between 15 and 30 degrees Celsius, it goes like every degree instead of every 5 degrees. You can get really granular about what the partial pressure of water is at 21 degrees versus 20, et cetera, et cetera. Okay. So this is Appendix B. We're very quickly in the next chapter going to start getting into Appendix C, and then later in the year we'll do Appendices D and E. These are all really useful resources for information to solve various types of problems. Okay, here is a problem that I've written here. 800 milliliters of hydrogen gas were collected over water at 21 degrees Celsius and 1 atmosphere. How many moles of hydrogen gas did I collect? Okay, well, if I was not accounting for the vapor pressure of water, if I was just assuming that all of the hydrogen, all of the gas in that sample in a graduated cylinder was hydrogen, I would just simply solve the ideal gas equation for N. I would plug in the numbers, 1 atmosphere, 0.8 liters, 800 mils, the ideal gas constant, and then because it's at 25 degrees Celsius, it would be 294 kelvin. And then I would solve for the number of moles of hydrogen, and it would tell me that I have 33.1 millimoles, or 0.0331 moles. Well, that turns out to be incorrect because not all of the gas in that cylinder is hydrogen. And so let's actually do it. Let's actually do the correct calculation. The first thing I need to do is look in the back of the book at Appendix B and find out what the partial pressure of water, what the vapor pressure of water is at 21 degrees Celsius. And it tells me that it is 18.7 torr. Okay, so now I have to do a little pressure correction. Instead of 1 atmosphere, it's not going to be 1 atmosphere of hydrogen. It's going to be less because of the vapor pressure of water. And so I've got to do that correction. I take 760 torr, which is 1 atmosphere, subtract out the vapor pressure of water. That gives me 741.3 torr of hydrogen. When I convert that back into atmospheres, that is now 0.975 atmospheres instead of 1 atmosphere. Now I plug that back into the equation to solve for N, and I get 0.0323 moles of nitrogen instead of 0.0331 moles of nitrogen. Okay, that's the end of the slides. So the QOD coming up is going to cover topics that were in this slide presentation, and there are some suggested problems as well. Thanks so much for watching.